Hi, we're the Adversarial Machine Learning Against Voice Assistant Systems group. We're supervised by Dr. Ying Chen.
Hi, I'm Selena.
Hi, I'm David.
Hi, I'm Sarab. So a little background on this project. This project aims to use adversarial machine learning techniques to attack voice assistant systems such as Google Home and Alexis. These devices are very commonly used nowadays. It can tell you the time, weather, control the lights, and a lot more. Basically, they hear your voice using microphones and understand what you said using machine learning techniques and answer your requests. We will try to attack these devices by adding a small perturbation to your voice. Our objective for this project, so during this project, we wanted to study the security of voice assistant systems. More specifically, we wanted to generate and analyze adversarial audio samples to attack speaker recognition systems, and then evaluate the performance under attack.
The first thing that we had to do was identify a speaker recognition model to attack. We ended up choosing the X-Vector model, which is a state-of-the-art model that is built using deep neural networks. One advantage of this model is that many proprietary closed-source speaker recognition models are built off of the same concept, so this gives us a look into some of the real-world applications. We implemented the X-Vector model in TensorFlow, which is a machine learning framework that provides us many useful tools that helped us build and examine our model. The first half of our project focused on untargeted attacks. The goal of an untargeted attack is to incite a misclassification. For example, if I were to say something, the model would predict that the speaker is anybody else. While this doesn't seem very useful at first glance, we could consider a situation where speaker recognition is used for authentication. Say we have a voice assistant system that internally has a list of authenticated users that are able to, say, request bank transactions. With an untargeted attack, I could trick the system into thinking that I am one of those authenticated users. We perform our attacks by adding a small perturbation to the original audio using the fast gradient sine method. With the fast gradient sine method, we determine what kind of noise we can add to most negatively impact the model's accuracy. We varied the strength of this perturbation, which we'll discuss more later in the results. The second half of our project focused on targeted attacks. The goal of a targeted attack is effectively to imitate a particular speaker. These attacks are much more powerful since they can be used for targeted identity theft, but are also much more difficult to perform. These attacks are done iteratively by adding noise to the original audio sample until it's recognized as a target speaker. Essentially, at each step, we add some noise to the audio, see what the model recognizes the speaker as, then add more noise such that it sounds more similar to the target.
So here you can see some of the results of our untargeted attacks. As David briefly mentioned before, we were able to vary the strength of these attacks by scaling them with a variable that we will call epsilon. The plot on the left shows different epsilon values and their corresponding noise level in decibels. You can see that as the epsilon value increases, the average noise level increases as well and becomes less negative. The plot on the right shows different epsilon values and the corresponding model accuracy under attack. As the epsilon value increases, and therefore the noise level increases as well, the model accuracy decreases. You can see that even at the smallest epsilon value, the distortion of the sample already decreased the model accuracy by about 20%. If we play the two samples linked here, you can very clearly hear the difference in noise levels from samples generated with the lowest and highest epsilon value.
They had to learn to work on the
In order to determine the threshold at which noise levels could first be determined, we conducted a survey, which allowed us to get a more subjective view of our data. We uploaded 9 different adversarial samples onto our website, each corresponding to a different epsilon value, and then asked people to listen and vote on which epsilon they could first hear the noise in our sample. You can see from this pie chart that the earliest detection was at an epsilon value of 0.000316, which corresponds to a model accuracy of about 30%. And these are the results of our targeted attack. Here's one of the samples that we generated. It's one of the 9 that we have put on our website.
If you can run a computer, you can.
So the graph we generated shows the average noise injected into a sample when trying to imitate the corresponding speaker. So for this graph specifically, we chose a sample size of 50 speakers. The average noise level for these 50 speakers was about negative 21.6 decibels, which if compared to our untargeted attacks, roughly correlates to an epsilon value of 0.0316, which was easily heard by the human ear according to our survey results. So currently, our model simply generates adversarial samples and evaluates their efficacy. For future work, we'd like to conduct an over-the-air attack, in which case we would have to consider the room impulse response, which is essentially how our audio would be affected by the environment in which we launched our attack. By taking the room impulse response into account, we would be able to make our attack as efficient as possible. We would also like to disguise our attacks to produce greater unpredictability. So right now, as you could hear in the sound files that we've played, it's fairly easy to hear the noise that we've injected into our adversarial samples. By disguising our attacks, for example, embedding the noise within a song, it would make it very hard for the human ear to identify the attack, but the speaker recognition system would still pick it up.
Thank you.